All right, buddy. Class recording has begun. So, as we just saw on the calendar, last Friday we began talking about the quantum mechanical model of the atom. And we said the previous week's worth of work dealing with atomic mass and average atomic mass and how these different atoms compare to one another deals basically with the nucleus of the atom because it deals with mass. And most of the mass of the atom is in the nucleus. So the remaining section of this unit, about the next week and a half, deals a lot with electrons because they don't contribute much to the mass of the atom, but they do contribute a lot to the behavior of the atom. And so that's what we're going to get into starting, we started Friday and stuff like that. So here's what I want you to do. Outline from last week that said the quantum mechanical model of the atom, all right? We got through, like I said, about the first 2/3 of the front side, and a lot of that dealt with the Bohr model of the atom. So here are the objectives from last Friday. We didn't get to all of them, but the first two, whether it will show up or not, there. The first two deal with the Bohr model of the atom. So I want you to take 30 seconds, talk to the person next to you about these two objectives from last Friday. The main aspects of the Bohr model and the limitations of the Bohr model. So discuss, 30 seconds, we'll come back and discuss together. Go. All right, so let's discuss. First, what does the Bohr model of an atom look like? If you had to draw me a Bohr model of an atom, what would it look like? Eris, go ahead.
The nucleus of the atom, and then there's shells with electrons on.
Kind of like that, right? Okay, where we have the nucleus in the middle, and then these electrons around the outside in these very defined shells. All right, or orbits, kind of like planets going around the sun. All right, so why are those orbits important? What did Bohr say those orbits represent about those electrons? Mark, good.
Different energy levels, but different amounts of energy in the electrons.
Different amounts of energy that those electrons possess, or different energy levels. All right, so is an electron stuck in its orbit?
No.
No, it can move around. But what does it have to do in order to move around?
Has to gain or lose energy.
Has to gain or lose energy. And the analogy, the example that we used to explain that kind of looked like what?
Ladder.
In the real world, what did it look like?
A ladder.
A ladder, right? So we said that these electrons could exist in these energy levels or these orbits, and it could move up or it could move down, but it has to either gain energy to move up the ladder or lose energy to move down the ladder. All right? And this is how these are explanations. These are theories that Bohr is using to try to explain actual behavior. All right? We won't tell you what the behavior is right now. That's more of a chemistry thing, okay? But keep in mind, this is a theory, and out of that theory comes a model to explain his theory. Right? So getting back to some of those terms that we introduced earlier in the year. Now, is Bohr's model correct?
Yes, but only for hydrogen.
Works good for hydrogen, right? But once we throw another electron and more protons into the mix, not so much. Not that it's really bad. It's not a terrible model, but it doesn't explain everything. Okay? Kind of like, I guess I kind of thought of this, right? It's kind of like, you guys know Pinewood Derby? Soapbox Derby. You ever see the Soapbox Derby? Right? These kids build cars out of like box and they ride them down the hill, you know? Is that a reasonable facsimile of a car? It's got wheels, you sit in it, you can drive it, right? But is it a real car? Doesn't explain everything, right? Or kind of like a go-kart, right? A go-kart is a lot like a car. It's pretty close to what a car looks like, but maybe not exactly right, okay? And that's what Bohr's model was like. It explained a lot of things. It did a good job of explaining certain things, but just didn't quite get there, okay? So if we have a model that doesn't explain everything, what do we have to do? Somebody else besides these two could probably answer, right? Laura? Get a new one, right? Or change the one we have, okay? So, in order to do that, though, we have to make new observations, come up with new information to try and explain what we're seeing. And that starts with this French guy, de Broglie. So, before de Broglie, another guy you may have heard of, Einstein, ever hear of him? He makes a discovery about light. And he says that light could actually sometimes behave like a wave, kind of like a water wave. Not exactly, but kind of. But in certain situations, light behaves like it's made of a bunch of pieces, kind of like rain or something like that. Does that make sense? Okay? If it doesn't, don't worry about it. It's pretty advanced stuff. But Einstein proposes this theory about light. So de Broglie goes, okay, hold on a second. If light has what we refer to as a dual nature, that sometimes it behaves like a wave, and sometimes it behaves like a bunch of little pieces, parts, all right? That, well, if light can do that, maybe actual matter can do that as well. That most of the time matter behaves like it's a solid piece of something. But under certain circumstances, matter can behave like a wave or like energy. All right? Building off of Einstein's ideas, kind of like E equals mc squared and some of those things that we'll introduce a little bit later on. Okay? So de Broglie goes, well, wait a minute. Maybe matter isn't matter the way we think of it. Maybe it isn't like a solid piece of something that can never change form. Maybe, depending on the circumstances, it's actually not solid. It's not matter the way we think of it. Okay? So, we then take, or other scientists then take this idea and kind of run with it. Now, keep in mind, time frame. Okay? We didn't learn about electrons until about 1897. This is about 1915-ish, all right? So we've come a long way, and you're only about 15, 16, 17, 18 years, all right? But these things keep happening in sequential order because somebody proposes something, it seems to work pretty good at the beginning, but then not so much, and then we have to come up with something new. So de Broglie goes and says, okay, well, maybe matter isn't matter the way we think of it. And then this guy, Heisenberg, comes along and proposes his uncertainty principle. So, Heisenberg shows that because an electron is matter, but matter isn't sometimes matter the way we think of it, that we will never know exactly where and how fast an electron is going. This is referred to as Heisenberg's uncertainty principle. Mathematically, it is impossible to know exactly where an electron is and how fast it's going at the same time. you can either know where an electron is, but not how fast it's going, or you can know how fast it's going, but not exactly where it is, but you can't know both at the same time. Okay? Think about it this way. Hopefully you guys haven't encountered this yet, because none of you are any of you driving yet? Even learner's permit? Okay, good. Right. Anyway, so police officer is standing on the side of the car. He's got his little radar gun, right? Okay? And he has a little radar gun, and he clocks you going, not you necessarily, right, but he clocks a car speeding, going a certain speed that he can use to write a ticket because it's over the speed limit. Can he say exactly where you were when he clocked that you as that speed? He doesn't know exactly where it happened, right? He knows how fast you were going, but not exactly where, okay? But in another law enforcement idea, right? You guys know about the little cameras that they have at some intersections to catch people who run the red light, okay? That camera takes a picture of your car, and it shows that the light was red as you were going through it. Does that picture show how fast you were going when you ran the red light? It shows where you are, but not necessarily how fast you were going. Okay? Now, in the big world, we can sort of resolve those two things together. But in an electron standpoint, that's hard to do. To find out, not hard, it's impossible for us to do. To find out how fast something is going and where it is at the same time. If you take a picture, it freezes everything in time, and you can say the electron was there, 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 there. You can't really take a picture of an atom, but if you took a picture, you could say, oh, electrons are there, 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 and there, but you don't know how fast they were going at the time. Or you could record the speed of the electron, but you don't exactly know where that happened. Mathematically, it's impossible for us to know both, and that refers to Heisenberg's uncertainty principle. Okay? So another scientist takes Heisenberg's uncertainty principle and runs with that. His name is Schrödinger. Okay? Check out Schrödinger. Doesn't he look like a classic scientist guy? I mean, with his like round glasses and his bow tie, you know? All right? So, and he's German. So actually, I don't know if he's German. He might be Austrian. Can't say for sure. I don't want you to say he's German, but he's got a little German-sounding name, right? Schrödinger. Okay. So Schrödinger's wave equation. This symbol over here on the side is a Greek letter. It's the Greek letter psi. Okay. Kind of looks like a pitchfork. This is the symbol that we use to represent Schrödinger's wave equation. So, what does Schrödinger's wave equation say? Schrödinger, instead of drawing a picture of the atom, his model is not based on a physical representation of the atom, it's based on a mathematical equation. And what that mathematical equation says is that I'm never going to know exactly where an electron is, but through mathematical manipulations of actual data, I can give you a probability that the electron will be in a certain spot. I can't guarantee that the electron will be anywhere specifically, but I can give you a pretty good idea that I think it's going to be in a certain spot around the nucleus. And we refer to that as probability. Schrödinger's equations take the model of an atom from a picture representing the pieces parts to almost like a bar graph that represents probabilities. Okay? Going back to your bullseye lab that you did last week, one of the questions says, when you drop the marble, do you know where it's going to land? No. You were trying to hit it in the middle, but as you saw from all the marks it left on the target, you don't hit the middle all the time. But are there certain areas that if you had to make a guess, you could guess, it probably is going to land somewhere in this circle? Could you make that guess? Yeah. Would it be right all the time? Not necessarily, but we can talk about the probability. Okay? Good there? So, there's still this idea of quantization and that these locations apply to certain amount of energies, but whereas Bohr said electrons are on the rungs of a ladder, it's either here or here or here, Schrödinger is saying, no, that's not it. I can give you a good guess of where electrons are, but I can't guarantee anything. And this is how we have come to perceive the atom. Okay? It is not a defined system of protons, neutrons, and electrons. It is a sort of continuously changing arrangements of protons, neutrons, and electrons, especially the electrons. Okay? And we don't know exactly where those electrons are, but we got a pretty good guess. All right? So, we refer to these areas of high probability as orbitals. And we will talk about orbitals more in the next outline. We'll talk a lot about orbitals in the next outline. Schrödinger's wave equation allows us to calculate the chances or the probability that electrons exist in a certain area. These dots represent a possible location for an electron. Is it where an electron is? No. Is it a possible location? Yes. Notice the possible locations start congregating in certain areas. What we find out is that the possibility exists that an electron could be anywhere around the nucleus. But the probability exists that it's within a certain area. Does that make sense? It's kind of like you and where you are. Okay? Is it possible that when you left your house this morning, you stole a car and were on your way to Mexico? Is it possible? Yeah. Is it probable? No. If your mom is trying to find you, are there certain places she would look first before other places? Was the first place she would call Border Patrol down in Texas because you're driving to Mexico? Is that the first place she's going to look? Probably not, right? First place she's going to look is in your room, right? Or at school or at your friend's house, right? It's possible that electrons could exist anywhere, but it's more likely that they exist in certain spots. Does that make sense? So what does that do to our model of the atom? Okay, well, here's the progression. We kind of talked about this a little on Friday before we got into Bohr's model, right? Here's Dalton's model of the atom. What does Dalton's model of the atom look like? What did we say Dalton would think an atom looks like? Chris? A little indestructible sphere, right? Because he said that there's nothing smaller than an atom, right? It doesn't have any parts. It's the smallest thing out there. But then Thomson comes along, right, and comes up with the idea that there are negatively charged particles. So he comes up with his plum pudding model, right? Where we said kind of like almost like a chocolate chip cookie, right? Where the cookie part is the positive material of the atom, but the chocolate chips are these negative pieces that he we eventually call electrons. But then Rutherford discovers the nucleus, right? And takes all of that positive material and puts it in a very small space right in the middle. The electrons just exist somewhere around the outside. But then Bohr says, no. Electrons exist in these nice defined orbits. But then we realize that that's not the case either. And then Schrödinger comes up with these ideas called electron clouds or electron orbitals. They're not orbits, they're orbitals. Because we don't know that electrons are going to be in a certain spot, but we can give a pretty good guess that they're going to be there. Does that make sense? So this is our progression of the atomic model. What people think, or what scientists, or whatever, what people think an atom is going to look like. Why are there 5 different pictures?
Because it's changed over time because nobody was exactly sure, or necessarily is exactly sure even today what it looks like.
Not so much that people weren't sure. Why does the picture keep changing? Chris?
They found out more about the atom?
We find out more about it, right? Like I said, Chris, we go from Dalton to Thomson because what happens?
Thomson found that they were positive and negative.
Thomson finds there's positive and negative charges. So we can't have this nice solid sphere anymore. It's got to represent both parts, right? So we keep finding new information that causes us to keep changing this picture. Okay? Good there? All right. So let's go here and let's talk a little bit about Schrödinger's model. Okay? Up on the board, is a map showing population distribution in the United States and Puerto Rico based off of census data. Okay? So, I always like maps like this. I think they're really, really cool. And especially like if you ever fly at night, like where all the lights congregate, that's generally where the people are, Okay? So, where were we? Different map, I'll look at it. The last census that we did in 2010, I believe, said that we had somewhere in the area of 308 million people in the United States. But, as we can see by the map, and because you just know this because you know, are all of those 308 million people distributed evenly across the country? Absolutely not, right? We see here, right, that there are areas represented by the lighter spots that represent more people. And then there's areas like out here in Montana and Idaho where there's nobody, okay? So kind of like an atom, is it possible that a person could live anywhere within the United States? Is it possible? Yes. Is it probable? No. People generally live in certain areas. Now there's reasons why people live there, right? What's one of the biggest reasons why people live where they live?
Water.
Water, right? Okay. That's generally why people live where they live. Okay? But is it possible that people could live out here? Sure, right? It's possible. It's not probable. And that's what we get into a little bit more with this picture of the atom. Okay? So, what do we call these probable locations where people live in this country? Cities. Cities, right? But even within a city, are the people distributed nice and evenly? No, right? If we go here, okay, to this map, there we go. So here's this distribution of population within the country, right, by state, right? But then we could talk about it a little more as far as country subdivision. Who wants to know the subdivision of Kansas? No. Iowa. I'm sure that's pretty exciting. So, okay, but that's a little too far. So even within let's do this. Okay, sorry, zoom back out. If we go back to the national view, right? Iowa is all one color, right? But are there parts within Iowa that are more populated than other parts? Relatively speaking, all right, let's face it, nothing in Iowa is real populated, okay? But are there other parts in Iowa that are more populated than other parts? Sure, right? Why don't we go someplace that we know a little bit better, right? Let's go to Ohio, okay? Let's go to county, okay? So there we are, right? Darker colors, more people, lighter colors, less people, right? There are parts of Ohio where not a lot of people live, right? But then there are certain parts of Ohio where lots of people live. If we go a little bit closer, right, go to the county subdivision, this is all census data, right? We'll zoom in a little bit closer, right? And let's look at an area that we're a little more familiar with, right? This area up here, okay? That even around Cleveland, right? Look, there's little pockets of yellow, right? In the greater Cleveland area. What might those spaces represent? Where would there be low population density even in the city of Cleveland? Chris?
Forest.
Forests like Park, right? Metro parks, what else?
In the middle of a river or a small lake.
Middle of the river or a small pond or something like that, right? That even areas that really look to be densely populated, when you look closer, there's even more areas within that densely populated area that maybe aren't so densely populated. Okay? Good with this idea? All right. I am going to stop us there for today because that would take us into the beginning of the next outline, and I don't think I want to start that. I'd rather do that all in one day. Okay? So why don't we wrap it up for there? Okay? If you did not have a chance to read these pages about the model of the atom, please make sure you do that tonight, okay? And then there are a couple of problems from the book that deal with the uncertainty idea and stuff that we just talked about with Heisenberg and Schrodinger and stuff like that. Okay? Tomorrow we will get into quantum numbers. Woo!